Have you ever stared at one of those flight maps on the screen in front of you and just wondered, how does a tiny plane actually find its way across a massive, featureless ocean? Well, it's not just about pointing the nose in the right direction and hoping for the best. It's this incredible dance of geometry, magnetism, and some seriously clever mental math. Today, we're going to pull back the curtain on the unseen science of air navigation and really understand how pilots conquer the globe.
And it all comes down to this one single question. How do you draw a straight line on a spinning ball? It sounds so simple, right? But when your destination is thousands of miles away on a curved surface, the very definition of a straight line gets really complicated. This one question is the key to unlocking everything that follows.
All right, welcome to your pre-flight briefing. Before the wheels even think about leaving the ground, the most critical part of the journey is already happening. It all starts right here, with a map, a destination, and a plan to connect those two dots. And that plan is written in the universal language of location, the grid. You know, latitude and longitude? Think of it like this. Latitude lines are the rungs on a ladder running east-west, and longitude lines run north-south, from pole to pole. Now, this system is so precise it can pinpoint a spot on Earth to within half a meter. But here's the catch. Get it wrong by just a fraction of a degree, and you could miss your destination by hundreds of miles. The stakes are pretty high. So you've got your start and endpoints plotted on the map. Now you face your first big decision. What kind of line do you actually draw between them? And believe it or not, there are two main choices here, and they represent this classic trade-off between pure efficiency and simple practicality. Okay, so on the left, you're looking at a great circle. This is the absolute shortest path between 2 points on a sphere. It's what you'd get if you stretched a string really tight on a globe. But notice how its angle keeps changing as it crosses the longitude lines. To fly it, you have to be constantly adjusting your heading. Now look to the right. That's a rhumb line. It's a longer path for sure, but it has one beautifully simple advantage. You just follow a single, constant compass heading the entire way. And this quote just nails why, for centuries, the rhumb line was king. Before we had powerful computers that could calculate all those great circle heading changes on the fly, sailors and early aviators went for the simpler, safer bet. Holding one steady course was just way more practical, even if it meant a longer trip. Okay, so we're off the ground now and we're relying on our instruments. The most basic one of all, the magnetic compass. But this simple little needle? Well, it's got a few secrets. Turns out, it doesn't really point where you think it does, and there are all these invisible forces trying to lead you astray. So first up is something called variation. So your compass needle doesn't actually point to the geographic North Pole, the spot we call true north. Nope, it points to magnetic north, which is this wandering spot up in northern Canada that's always on the move. That difference between true north and magnetic north is called variation, and pilots have to add or subtract this value, which, by the way, changes depending on where they are in the world. But wait, it gets even more complex. The second error is called deviation, and this one comes from the aircraft itself. The plane's metal body, all its electronics, the engines, they create their own little magnetic fields that pull the compass needle away from magnetic north. So a pilot has to correct for variation just to find magnetic north, and then they have to correct again for deviation just to get an accurate reading from their own instrument. So how on earth do they keep all of this straight in their heads? With clever little memory aids that have been passed down for generations. This is one of the most famous ones. When you're correcting from a true heading to a magnetic one, if the variation is to the west, the magnetic number will be best, meaning it'll be bigger. If the variation is east, the magnetic number will be least, or smaller. It's simple, but incredibly effective. So you've planned your route, you've corrected your compass, but a forecast is just a forecast, right? The wind is never exactly what you expect, and pretty soon you realize you're off course. You don't have a calculator, you don't have a computer. What do? Well, you use a brilliant little piece of mental math. This is the 1 in 60 rule, and it is a pilot's best friend. It's this beautifully simple approximation of trigonometry that works without any complex tools. Basically, if you've flown for 60 miles and you find you're 1 mile off track, your error is 1 degree. If you're 2 miles off track, your error is 2 degrees. You see, it lets a pilot quickly calculate their track error just by looking out the window and checking their map. So how does a pilot actually use this? Okay, let's say you figure out you're 8 degrees off track. First, you turn 8 degrees back towards your intended course. That stops you from drifting any further away and gets you flying parallel to where you should have been.
Then you turn another 8 degrees. This double correction creates a perfect intercept angle that guides you smoothly right back onto your original route. It's really elegant.
All right, let's bring all this into the modern era. We've just navigated across the globe using nothing but a compass, a map, and some clever geometry. So how does this old school knowledge apply to the high-tech glass cockpits of today? Well, today's cockpits are just packed with incredible technology. You've got GPS, the Global Positioning System. You've got Flight Management Systems, or FMS, and Inertial Reference Systems, the IRS. They do all the heavy lifting. They handle all these complex calculations instantly and with stunning precision. They figure out the great circle routes, they account for variation automatically, and they always know exactly where the aircraft is, down to the meter.
So you might be asking, why do pilots still spend hundreds of hours mastering all these manual techniques? Because, as the source material reminds us, technology can, and sometimes does, fail. And when the screens go dark, it's these fundamental skills, the deep knowledge of the Earth, the compass, and the 1 in 60 rule that are going to get you home safely. When you think about it, the principles of navigation are this hidden framework that makes global travel even possible. They just work perfectly, invisibly, every single day. And it kind of makes you wonder, what other unseen rules, what other elegant mathematics and clever shortcuts are shaping the world all around you, guiding your own journey in ways you've never even noticed?